We live in a world of molecules interacting with other molecules. Why do some reactions go fast while others take place very slowly? What factors govern the rates of reactions? Can we take a slow reaction and speed it up? Can we slow a fast one down? Molecules move around, collide, and sometimes react. To study this molecular behavior, we must probe a science called chemical kinetics. Here's an example of a reaction that goes very fast. What about one that takes more time? Roads, dams, bridges, churches, houses, and offices. There's chemistry in all that concrete. Trucked in slowly turning drums, the mixture of water and cement and gravel cannot set into concrete until it's spread on site. Boxed in place, it will be left to react slowly, water and cement reacting to produce microscopic bridges of calcium silicate with the gravel. If wooden forms are not left in place long enough, if not enough time is allowed for reaction completion, the consequences can be disastrous. In Virginia in 1973, the rubble remains of a partially collapsed apartment complex. 14 died. Too much haste for the slow reaction rate, which makes hard concrete. The rate of any chemical reaction depends on several factors. Don Showalter.
Let's take a look at one of the most common reactions of all, simple burning. Here I have a piece of wood. We all know that wood, if dry, will burn readily in air. Remember, air is about 21% oxygen. It's not burning. Oh, we've got to warm it up, don't we, to get it going. Let me warm it up with this match. Oh, I warm it up. The oxygen of the air reacts with the wood. There it starts going. Now that's burning pretty well, but not really well. I wonder if it'll burn any better in this 100% oxygen. Well, let's see. Oh, look at that. The rate of reaction is drastically increased. Now, what does this tell us? Well, there's a couple of things. The rate of the reaction is increased with increased temperature. Remember the match. And also, the rate of the reaction is increased with increased concentration of ingredients. Remember, 20% oxygen, 100% oxygen.
Increased temperature and concentration speed up reactions. Are there other general ways of speeding them up? One way, employed in most reactions in the chemical industry, involves using substances called catalysts. To see exactly how a catalyst affects reaction rates, let's first try a reaction and then add a catalyst.
Here I have a white powder, sodium potassium tartrate. It's about 30 grams. I want to dissolve that into this warm distilled water. Water's at about 70 degrees Celsius. Now, that's a fairly large molecule. I want to perform a chemical reaction for you where I break this big molecule down, degrade it. Now, the way I do that is by adding hydrogen peroxide, a fairly strengthy solution, 30% hydrogen peroxide. Now, if there is a reaction, you should be able to see carbon dioxide given off, bubbles. Let's see if it happens. I'll pour it in there. Well, not many bubbles. Even though I heated it, and we know that heat increases the rate of a reaction, it didn't speed it up. So what else can we try? How about a catalyst? Let's add a catalyst. Now, I'll put it into this container just in case it does go pretty fast. Now, here's the catalyst. It's a solution of cobalt chloride. Let's add that to this reaction mixture and see what happens. Now, a catalyst will speed up a chemical reaction, and look what's happening. The carbon dioxide bubbles are being given off. But one other stipulation for a catalyst is that it must be the same at the end as it was at the beginning. Look at the rate of reaction. Notice it's green, so the catalyst is actually taking part in the reaction. Look at the steam being given off here. Oh, now if it's a true catalyst, what should happen? It should be the same at the end as it was at the beginning. Look at the color. It's back to that original pink color. What's a catalyst? It speeds up a chemical reaction, but it must be the same at the end of the reaction as it was at the beginning. It's pink again.
We have seen 3 ways to speed up a reaction: increased temperature, increased concentration, and the use of a catalyst. To understand how these factors govern the speed of a reaction, we need to look at molecular motion. Like most other objects, molecules move around, and like every other moving object, they possess kinetic energy, the energy of motion. The faster objects or molecules move, the more kinetic energy they have. This kinetic energy can be transformed into other kinds of energy. For example, when 2 cars crash, the kinetic energy abruptly changes into sound, heat, and the kinetic energy of flying debris. If we could peer into the molecular world, we would see a blur of frenetic activity, randomly moving molecules colliding with one another. When molecules meet, one of 2 things happens. They either bounce off each other like billiard balls, or their kinetic energy may be used to break bonds and make new ones. In the process, different molecules are formed. A chemical reaction has occurred. Let's look at a specific example. In one step in the formation of hydrogen bromide, hydrogen molecules collide with bromine atoms. If these particles collide with insufficient energy, they simply bounce off each other. If the particles collide with sufficient energy, a reaction will result. Let's see that in slow motion. The 2 particles approach each other and collide. An activated complex forms. Kinetic energy is converted into vibrational energy. An old bond weakens and breaks as a new one forms. The complex then splits to give the products: a molecule of hydrogen bromide and a hydrogen atom. Collision theory helps chemists understand how chemical reactions occur, even the most dramatic ones. But not all collisions result in a reaction. The colliding hydrogen and oxygen molecules in this balloon will not react unless you give them some additional energy. A far more dramatic hydrogen explosion took place on May 6, 1937, over New Jersey. The world's largest hydrogen blimp, the Hindenburg, was preparing to land after another safe Atlantic crossing. But an accidental spark provided the additional energy for a terrifying reaction.
Within seconds, there was a terrific explosion aft, and brilliant orange flames formed the backdrop for a tableau of death.
The Hindenburg's 7 million cubic feet of hydrogen gas had ignited. The energy needed by the hydrogen and oxygen molecules to react is called the activation energy. Activation energy is like an energy hill. Few reactions will occur unless they are given a push to get them over the hill. Here is an energy diagram showing the endothermic reaction between hydrogen and bromine. The reactants are on the left and the products are on the right. We can represent the activation energy as an energy hill separating reactants from products. In order to react, the colliding particles must have enough total kinetic energy to overcome the activation energy hill. An activated complex forms. Once the activation energy has been overcome, The complex splits and the reaction proceeds to completion. The products are formed. Collision theory explains the effect of increased concentration on reaction rates. With increased concentration, there's an increase in the total number of collisions. This means more collisions between energetic molecules, so more get over the energy hill. This causes the reaction to speed up. Collision theory also explains the effect of temperature on reaction rates. When you heat a chemical system, the reactants gain energy and move faster. Now the collisions are more energetic, so more molecules will be successful in overcoming the energy hill. Again, more collisions result in a reaction, and the reaction rate is increased. If we could lower the activation energy hill, we would get the same effect without having to raise the temperature or increase the concentration. The lower the hill, the higher the reaction rate, because less energy is required for collisions to result in a reaction and the formation of product. One way to lower the energy hill is to add a catalyst. Then this reaction happens more rapidly. But sometimes we want to raise the energy hill and slow a reaction down. Food is shipped across America and around the world. Knowledge of the rates of food spoilage, the rates of chemical reactions in the food, is vital for our global economy. A far-off country like New Zealand, for example, is almost wholly dependent on overseas markets for its lamb and butter and cheese. It needs to be able to transport food without spoiling. Dr. Theodore Labuza.
The kinds of reactions that cause food to spoil are not very different than what chemists study in pure chemical solutions. What I always like to talk about food, it's the study of messy chemistry. And the reason I say that is that in a food which has so many different organic compounds and inorganic compounds together, there are lots and lots of different reactions that could cause spoilage.
Modern techniques of food preparation and refrigeration have greatly reduced spoilage. Still, the shopper might like further proof that reactions have been retarded, that food is as fresh as possible.
One of the more interesting things that we're doing in our laboratory here, which is an application of chemical kinetics, is the study of little devices that can be used to monitor time temperature when a food goes through a distribution cycle. Now, why do you want to do that? Well, since foods deteriorate at a faster rate when the temperature goes higher and at a slower rate when the temperature goes lower, if you had a device that could be put on a package that would essentially integrate the time temperature exposure and show a color change that could be related to the loss of quality of the food, then by simply picking up a package and looking at a device that may be on the package, you could tell how much more shelf life is left, so you'd know when to consume it.
To review, whether we are interested in the formation of concrete or in food spoiling, we need to understand the factors that govern reaction rates. Chemical reactions occur because molecules collide, but for a collision to result in a reaction, the colliding molecules must have enough energy to push them over the energy hill. This is called the activation energy. The speed of a chemical reaction can be increased by raising the temperature, increasing the concentration of the reactants, or by using a catalyst. Chemical kinetics can help explain why some reactions happen slowly and why others are fast.